Now,
Now it's okay, but yeah, okay.
okay.
Hmm.
What am I asking is there is a session going on right now, right? Max 2 session. Do anyone of you know is it ended or
It is still going on, sir.
it is still going on? Okay.
Sir,
Okay.
earlier your audio was good. Now I think fan noise or some disturbance is there.
Okay. Just a second. Now fine.
Yes, sir.
Yes, sir.
Yes, sir.
Okay. Okay. We will wait for some 2 to 3 minutes more. Okay. Let the max 2 session end by then, or else we will start slowly.
Sir, today what are we going to discuss?
So today we are going to discuss week 8,
Hmm.
the 4 lectures. Okay.
Nice. All four.
Yeah, most probably we'll cover all the 4.
Actually, sir, I was having a problem in CLT.
Yeah, we will discuss about CLT. We will do some problems.
Yes, sir, please.
Okay. Yeah. Uh, okay, let me share my screen meanwhile.
Sir, how was the difficulty level from week 9 onwards? Is it the same as week 4 to 8?
Huh. See, if you understand week 4 to 8 properly, then week 9, 10 were much more easier than compared to week 8. So maybe you will face some
Week
difficulty
eight
in
is
week 9. If you understand week 9 properly, then 10, 11 is pretty straightforward. Pretty straight, not straightforward, pretty easy thing to understand. It is basically on testing of hypothesis.
week 8 is actually tough, little bit.
Week 8, you might feel tough because there are many results that are being derived in the lectures.
And how they are derived, we don't know. I mean,
How they are derived, you
sir
don't
has
know.
derived, but it's very
Hmm.
lengthy. And
Okay, I will try to prove some of the proofs which
sir,
are
proof is not
left.
necessary for this, for the course point of view, but the end result is the main important, right?
Yeah, the end result is important. If you see, if you go on with only the end results, sometimes you might
No,
go
we
wrong.
will try to understand, but what sir said that it's okay if you not understand all the mathematical formulas which are being done while proving the results. So
Correct,
that's
correct,
why I was saying.
correct, correct. Ultimately, in this particular course, it is enough if you remember the end result or if you understand the end result.
Yes.
Yeah. Okay, we'll start at 8:10 exactly.
Sir, this week we faced difficulty while applying the concepts in questions.
Because more
Yes,
number
sir.
of concepts have been discussed within very short lecture.
3 to 4 lectures
Yeah, three to
are
four
there and
lectures and yeah, many
many topics
good
are
results.
discussed.
Yeah, many topics has been covered.
It's very
Sir, do we
difficult.
need to mug up all these formulas for the exam, or will it be giving like quiz one?
No need of mugging up formulas actually. The
Actually, sir,
results we won't give you, like some results like linear combination of some independent normals is normal. We won't give you that, but you should understand why the linear combination of independent normals is normal. You should remember that. But apart from that, all the PDFs, CDFs of every well-known distributions we will give you.
some
Even
new distributions are also there in this. Some
yeah,
new
new distributions. If
distributions.
it is necessary, we will give the new distributions like gamma, beta,
Yeah.
everything. If it is needed, we will give you the PDF, CDF with you. We will share it with you. No need to mug it up.
No.
Okay.
Sir, mugging up the formulas makes somehow the questions easier, and for fastly solve the questions.
But how much you will mug up?
Yeah,
There are tons of
the-
formulas. You won't mug up each formula.
Mhm.
And at the exam also, it won't be easy to remember all things.
and we forget the formula very next day.
Mhm. See, sometimes in my younger days, I used to listen this joke from my mathematics teacher. So some guy started mugging up things, even the basic things like 2 plus 2 is equals to 4. Okay. So he started mugging up 2 plus 2 is equals to 4, and also he started mugging up 2 times 2 is 4. Now he knows he mugged up these two, and he forgot what is 3 plus 3. Oh, no, he knows 3 plus 3 is 6, but he don't know what is 3 times 3. So with his base knowledge, what he thought is, I have studied that 2 plus 2 is 4, 2 times 2 is also 4, even though the sign changes, the value is same. So what he does is, even if the question is 3 times 3, he used to give answer as 6, and he claims that it is correct. So this is something like, if you mug up, sometimes you won't understand the actual concept, and you will end up falling into the trap of the question. Okay. Okay.
That's why
So
we
yeah.
invite you to explain the concept.
Is my screen visible?
Yes, yes, yes.
Okay. Okay, I guess it's already 8:10.
Yes, sir, we can start.
We will start slowly. Meanwhile, the people who are in Max 2 will also join. Okay. Okay, in this week, we started with moment generating function. We started studying about moment generating function. So what exactly is moment generating function is, if you have any random variable x, my screen is visible, right?
Yes, sir.
Yeah. So
Yes, sir.
if you take any random variable x, which is non-zero random variable. So what is non-zero random variable?
1, 2, 3.
Not only 1, 2, 3. So this particular random variable x takes values other
Minus
than
1
0.
also. Yes, minus 1, minus 2 also.
Uh, okay. So x is taking, suppose x is a non-zero random variable. So the Mgf of x is denoted as a mx of lambda. So again, you can see mx of lambda, this looks like a function. Yeah. So this particular Mgf is actually a function from R to R, real numbers to real numbers, defined as mx of lambda is equals to expected value of e to the power lambda x. So yeah, as we are talking, how this came, why this came, it's not important to us right now, but this particular thing is important to us. So what exactly this moment generating function is? So this is actually a function, and the function's output value is the expected value of e to the power lambda x. Okay. So yeah, that's it.
So what is lambda here?
So lambda is actually a value, input value. So for each input, so lambda comes from here, and expected value of e to the power lambda x is the output value.
So
So
lambda will be given to us, like,
if we wanted to ask questions on moment generating functions, we will give you the lambda. See, lambda is actually, see, the main usage of this particular function is to find the moments. Okay, moments like mean, variance, these are all called as moments. So mean is the
okay.
first moment. So we can actually compute using this moment generating function. So moment generating function. So it actually generates the moments.
Okay.
Okay.
Okay, sir.
So yeah, generates the moments, and those moments are pretty much related to our distribution. So mean is related to our distribution, one of the parameter. Variance is related to our distribution. And we will discuss other usage of moment generating function also while we go on. But as of now, this moment generating function is actually a function which is defined from real numbers to real numbers. where defined as mx of lambda is equals to expected value of e to the power lambda x. So some examples, let us see some examples. Suppose x is discrete with PMF fx and the range of x is x1, x2 and so on. Now, the moment generating function for this particular random variable will be, okay, what is the expected value?
It will
If
be
you
the
wanted to write,
summation of
yeah.
Probability times the sum
So what is the
value.
expected value of x if I wanted to find the
It is
expected
basically
value?
the
fx of
average
x1
long term.
Yeah, fx of x1
times the times x1
yeah
Hmm.
plus fx of x2
x2 times x2
times x2
and
and
so
so on.
on.
So if expected value of x is this, what is the expected value of e to the power lambda x? This will be like fx to x1 times e to the power lambda x1,
X1.
correct? So week 3 we might have studied this,
Hmm.
yes.
week 3 or week 4. So fx of x2 times e to the power lambda x2 and so on. So the same thing we will apply here and we will try to find the MGF of this discrete random variable.
So is there any kind of domain for lambda, or lambda can take any real values?
Lambda can take any real value. So this particular function is defined from real to real. So lambda can take any real value.
Okay.
Okay. So yeah, basically lambda belongs to real. Now let us try to find this MGF. So we use the same thing. So here it will be fx of x1 times e to the power lambda x1 plus fx of x2 e to the power lambda x2 plus and so on. So depends on the range of random variable x. Okay, if it is discrete. What if it is continuous with PDF fx and support tx? So if it is continuous, what is the expected value of x?
Minus infinity plus infinity integration.
So
X fx dx.
Integration
Minus infinity.
x belonging to tx, f of
support
x,
support x
x into f of x.
X
yeah
of h dx.
fx of x
into x.
times
X.
x dx, correct? So how should be if it is like expected value of e to the power lambda x?
S of x will write e to the power
So
lambda
x we will replace with
E to
here
the
x we
power.
will replace with e to the power lambda x, correct? So the same thing here also. So mx of lambda will be expected value of e to the power lambda x, and that will be x belongs to support of x, or here it is tx fx of x times e to the power lambda x dx. Okay, if it is discrete it will be like this, if it is continuous it will be like this, and we will take some examples, discrete examples and also continuous examples. So what if x is uniform between -1 and 1? So this is a discrete random variable. So you see this x takes -1 and +1 with probabilities. So
One
when
by
I say uniform with probabilities,
Half.
1/2 half.
yeah, equal probabilities. So there are two values, so half and half. So it will, the probability that x takes -1 is half, probability that x takes 1 is half. Now if I want, if so the range we have tx is -1 1, and also we know the PMF now. Fx of 1 is half, which is equals to fx of -1. So as this is discrete case, our MGF will be fx of 1 times e to the power lambda times 1. So see, look at here. So I am just writing, I am just replacing x1 with 1 and x2 with -1, or x1 with -1, x2 with 1. Okay. So if I replace it, I will get fx of 1 times e to the power lambda of 1 plus fx of -1 times e to the power lambda -1. Correct? What is
Yes.
fx of 1 and fx of minus 1? It will
1
be,
by 2.
so 1 by 2 times e to the power lambda plus 1 by 2 times e to the power minus lambda. So if you simplify this, e to the power lambda plus e to the power minus lambda by 2. Okay.
So just very small confusion here.
Hmm.
Fx refers to PDF, right?
Fx
of
refers
x.
to, yeah, here PMF.
PMF or PDF, right?
Hmm.
Okay.
Yeah. So as we are in discrete case, here it is probability mass
PMF.
function. Okay. Now if there is some other discrete distribution, like x can take values between 0, 1, 2, 3 with probabilities 1 by 3, 1 by 6, 1 by 4, 1 by 4. So if I wanted to write the moment generating function, so the probability that so fx of 0 times e to the power lambda times 0 plus fx times 1 times e to the power lambda times 1 plus fx times 2. So fx of 2 times e to the power lambda into 2 plus fx of 3 into e power lambda times 3. Correct? So the probabilities, the PMF is given. So 1 by 3 times e to the power 0 will be 1. So it is 1 plus 1 by 6 times e to the power lambda plus 1 by 4 times e to the power 2 lambda. So 1 by 4 because the probability that x takes value 2 is 1 by 4. So this is a PMF here. Plus fx of 3 is 1 by 4 times e to the power 3 lambda. So this will be the moment generating function for this particular distribution.
Sir,
So discrete distribution. Yeah.
here x is taking 0 also. No? At the beginning, I think we discussed that x should not take 0, non-zero.
No, x taking non-zero means x only taking 0. So x is taking
Okay.
0 with probability 1.
Okay.
So apart from this particular distribution, any other
So
distribution.
in range 0 may come.
In range 0 may come,
Okay.
but range should not be only 0.
Got it, sir. Got it. Thank you.
Okay.
So this is true for continuous. So okay, got it, sir. Thank you.
Yeah.
Got it.
So this is about discrete. What if our random variable x is continuous? So continuous means let us take exponential function. Okay. We just wanted to find the moment generating function of exponential function. So before that we need PMF of exponential. What will be the PMF of exponential? Theta.
Theta e to the power minus theta x.
So it will be theta into e to the power minus
Minus
theta
theta
x
x
when x is
greater than 0.
Greater than
Greater than 0.
0 otherwise. So the support of x is 0 to infinity.
Infinity.
Correct. So the support of x is x where x greater than 0. Now we have a support of x with us. We have fx of x with us, PDF with us, and also the support with us. Now we are ready to find the moment generating function. So the continuous case, so we have to take this thing. So the moment generating function will be integral. Okay, let's take one more page. So we have to find the integral x belongs to support of x, fx of x times e to the power lambda x dx. Correct? So this support of x is from 0 to infinite, and fx of x we have theta times e to the power minus theta into x into e to the power lambda x dx. Okay. So now we can bring theta outside. It will be like e power lambda minus theta into x dx. So now e to the power nx integral. So what is the e to the power nx integral?
E to the power nx divided by
divided by n.
Minus n, sir, I think.
No,
No, it's
Minus
n.
n.
No,
Okay,
it's
It
n
is
only.
n.
Yeah, okay, yes.
It is n only. So now here n is lambda minus theta. So this will be like theta e to the power lambda minus theta times x divided by lambda minus theta, and the limits are infinite and 0. Now you can see if my lambda minus theta, so if lambda is greater than theta, this when x tends to infinite, e to the power positive times infinite will go to infinite.
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 So if it goes to infinite, our MGF is, we say our MGF is not defined here. So for lambda greater than theta, our MGF is not defined. What if lambda is equals to theta? Even it falls in the same case. If lambda is equals
Undefined.
to, yeah. So it will be like it will go to infinite or undefined case. It will be like undefined.
Divided by 0, sir.
No, not divided by 0. Here itself you see if lambda is equals to theta, this will be like 0 and it will be like constant. And
Either
constant.
way, the denominator will be 0, right? Lambda minus theta becomes 0. So
Okay, even that is okay. But before that itself, if lambda is equals to theta, this will be 0 and e to the power 0 will be 1.
1.
So if you are integrating 0 to infinite with 1 dx, it will be infinite. X and x are taking infinite value will
Okay,
be
infinite. Yeah.
So here itself it is not defined.
okay.
So from here our condition is lambda should be less than theta. Okay, whatever the lambda here we have for exponential function. So we will see this, why I am proving this is because when you see the gamma distribution, so there we have given you the MGF of gamma and we said one thing, when alpha is equals to 1, this particular gamma distribution follows exponential.
Yeah, true.
And there we have given the parameter that lambda is somewhat greater than 1 by beta or something. Lambda is less than beta or something. Okay.
So could you please repeat?
We will discuss it there. Okay. So we have defined the gamma distribution in the lecture 3 and we said when we defined the MGF of gamma, and in that gamma distribution we said when alpha is equals to 1, so gamma has two parameters. Alpha is 1, actually gamma follows exponential function, exponential distribution. Okay. So for that it is important here. So the condition is lambda should be less than theta. So if lambda is less than theta, then what happens? So this will be like negative. So e to the power negative times infinite. So this will go to 0. So when x tends to 0, so when x goes to infinite, this particular e to the power negative times infinite will go to 0. Correct? E to the power negative and there is x. So if x goes to infinite, e to the power minus infinite, where will e to the power minus infinite go?
0.
0.
Minus infinite. It will go to 0. Yeah, it will tend to 0. So therefore, this will be theta times when at x is tending to infinite, this is 0 minus and x is 0. This will be
1 by lambda minus theta.
1 by lambda minus theta.
Minus theta.
And now we are very much closer. So this will be like theta by theta minus lambda. Correct?
Yes, sir.
So this minus sign, we can change it to theta minus lambda. And this is simply 1 by 1 minus lambda by theta. Ultimately, what we got is mx of lambda is equals to 1 by 1 minus lambda by theta. Okay. So this theta is the parameter of exponential function. Okay. If I call it beta, then this will be beta. 1 by 1 minus lambda by beta, right? So I am saying this is this will be useful for later result. So remember this now. So our exponential function, exponential distribution MGF will be 1 by 1 minus lambda by beta, where beta is the parameter of exponential distribution. Okay.
So why are you changing it to beta?
Why are we changing it? Because in lecture 3 SAR has used beta.
Oh,
So we are not changing it. I am just telling here it is initially I have taken it as theta. So we got 1 by 1 minus lambda by theta. If I have given you like beta, it would be like 1 by 1 minus lambda by beta. But the main idea is the parameter, the lambda is divided by the parameter of exponential distribution. Okay.
yes.
Okay. So if it is continuous, this is how we get the moment generating functions.
So in lambda less than theta, we are putting the constraint on lambda.
No,
Or
constraint on x.
no, like the condition that lambda is less than theta.
We are restricting lambda here.
Okay.
So
Now,
this
like we don't control theta, right?
We don't control theta. So this particular MGF is valid only for lambda less than or equals to less than theta. If lambda is greater than theta, MGF of x is MGF mx of lambda is not defined.
Wonderful.
Okay, lambda greater than or equals to theta, mx of lambda is not defined. If lambda is less than theta, mx of lambda is 1 by 1 minus lambda by theta. That's it. Okay.
Okay.
Yes.
So yeah, till now we have seen if I have given you the distribution, then how we find the moment generating function. And one important usage of this MGF function is if I have given you MGF, so the moment generating function of some random variable, then I can actually define the distribution. I can actually find the distribution of that particular random variable x. So that is one good usage of MGF. So using MGF, if you have MGF, we can uniquely determine a probability distribution. Okay, how do we do that? So if I have given you the MGF of the random variable x is like this. So by looking at the MGF itself, we can determine whether that is continuous random variable or discrete random variable. So you can see here the value is something like some value e to the power something plus there is some term e to the power 2 lambda plus something. So if it is sum of few e to the powers, then it is a discrete random variable. X is a discrete random variable. Okay, discrete
If it is
random
like
variable.
this, means if it is like addition of all terms.
Addition of few e to the powers different terms. So here our terms are e to the power minus lambda, e to the power 2 lambda, e to the power lambda, e to the power 5 lambda. We have 4 different terms. So if you have sum of few terms, e to the power terms, then the moment generating function actually determines actually the moment generating function is a discrete moment generating function for discrete random variable. So here x is discrete and takes values. So whatever you see in the e power, so e power x1 lambda, so just equate it, just compare it with fx of x1 e to the power x1 lambda plus fx of x2 e to the power x2 of lambda plus fx of x3 e to the power x3 of lambda plus fx of x4 e to the power x4 of lambda. So just compare this thing with this and find x1, x2, x3, x4 and then fx of x1, fx of x2, fx of x3 and fx of x4. So if we compare, we get x1, x2, x3, x4 as minus 1, 1, 2, 5. Okay. And with probabilities, the PMFs will be, so minus 1 with probability, fx of x1 is half.
By 2.
And fx of, okay, I should have written it here, but
1 by 8.
Nothing
1 by 8.
changes. So it's like, what is the probability of x taking value 1. That means fx of 1. So we need the value of fx of 1. Fx of 1 is 1 by 8. So x takes value 2 with probability 1 by 4. 5 with probability 1 by 8. Okay. So this is the distribution of x.
Sir, this is valid for
the-
only the discrete cases, right? In the continuous case, we cannot say from the NGF the distribution.
No, no,
Yeah,
no.
I was
We
also-
can say. See, if I have
From
if I have
from the previous case, can you say the distribution actually from the end result, like
see
from the result 1 by 1 minus lambda by theta? Can you say that it is the exponential distribution?
yes. So that is what I am saying, right?
How, sir?
So you want to prove, we want to go back. So
Yeah,
for
from
that
the
we need we need higher computations.
okay, means we cannot like in
Approve
hand
it.
compute.
It's not like 2-line proof or 3-line proof. Okay.
Okay,
have
computation
to-
means like in the programming, or we can do it by hand.
No, it requires something like 1 by 1 minus x expansion. First step is like step 1 is
Okay,
like
okay.
this expansion. You expand
Yeah,
this,
yeah.
and then
Okay, yeah.
you will look into moments and it will go like
Okay, okay, I
but
got it.
yeah, one usage. See, that is what I am telling, right? See, if you know the MGF, you can actually find the distribution, no matter whether it is continuous or discrete.
Okay, sir.
Using MGF, you can actually determine the probability distribution. Okay, that is the usage of MGF. So first usage is we have discussed it. It actually used for finding moments like mean, variance, etc. So if you expand that moment generating function, so if you expand this expected value of e to the power lambda x, so using the expansion of e to the power x, so there you can actually find the moments, mean, variance, and everything.
Yes.
And one more usage is, if you know the moment generating function, you can actually directly determine the probability distribution. So this is like a one-to-one function. MGF2 distribution is a one-to-one function. Okay, for single
Okay.
MGF, we have only one single probability distribution. And also it is bijection, maybe you can say bijection. So for single probability distribution, you only have unique MGF. So you don't have two MGFs for one distribution.
I have a
Okay, sir.
question here.
Got it.
Yeah.
When we say we can derive it, but where will you get the moment generation function from? If we have data and you have moment generating function, then we actually have the possibility of getting the PMF. Okay, agreed. But where will I get the MGF from?
Where do you get the MGF from?
How will I get the data on MGF itself?
No, you have your data, and from that data you wanted to get MGF. Is that what you meant?
No, if I have the data, I can get the PMF.
Okay.
Correct. If I have the data, if I have the PMF, why do I need the MGF for getting the PMF? What's the advantage? Like, why? When is it beneficial? Okay, I can get the data, but when is it really useful to me?
When it is really useful is, see, if you are looking at single random variables, you can actually look at the data and you can actually get the PMFs or PDFs. So if it is combination or functions of random variables, like let's say sum of random variables or product of random variables, or if you have some 10 random variables which follow different distributions. So if I wanted to combinedly look at, or if I wanted to look at the sum of those random variables, directly getting the distribution is difficult.
Right.
Okay. So for that, what we do is, from the different, so let us say you have x follows some normal, y follows some uniform, like this, and you wanted the distribution of x plus y or x times y. So you want to look at the distribution. It may not be easier to get it directly. May not be easier. I don't say it is difficult. It may not be easier. But using MGFs, if you know this moment generating function and this moment generating function, or the sum you see. Or it's not about only two random variables. If you have some, see, one good approximation is if you have some n random variables, and each of n random variables follows normal but with different mean and different standard deviation. And you wanted to look at the sum. So how will the sum behave? Okay, what is the distribution of sum of these n random variables? So getting directly the distribution is a lot more difficult than using MGFs.
Okay.
Okay, so there this particular MGFs are pretty much useful in.
Okay.
Okay.
Thank you.
I
So this
have
is
query, sir.
one usage I said. So there might be many usage of MGFs.
Hello. Hello.
Yeah, Nikhil, you are audible.
Sir, what is the significance of lambda here? Why not mx of directly x? What is lambda doing in the MGF function?
What is lambda doing in? See, x actually belongs to the support of x actually belongs to the range of x or support of x. Okay.
We
And
are
here,
anyway multiplying by x to the lambda.
huh?
In e to the power lambda x, we are anyway using x.
We are using x. So you to use the different parameter or different variable, we use lambda. So this particular lambda actually comes from here. Comes from here. So when you define a function, you define the domain and you define the codomain, right? And so you remember functions f of x.
Yes.
So this particular x, so instead of using x, we are using lambda here. So some people will use t. Instead of lambda, many books will use t. Okay. It's just the variable we use as an input of this particular function. Okay. Okay.
Even though we consider lambda as a variable, but while finding expectation, we integrate with respect to x, is it?
With integrate with respect to x only. See, the integration will happen with respect to x only.
Yeah, but both lambda and x are variables here, right?
Lambda is actually, lambda is a variable, but we consider it as a constant here.
We assign a value, right, sir?
It's a parameter.
We assign a value.
We assign a value to lambda.
Parameter, okay.
Yeah. Okay.
So it can be 1, 2, 3.
It can be 1, 2, 3, any real number.
If it is 1, then x will be the parameter.
Hmm?
If lambda is 1, then only x will be the parameter, no, sir?
If lambda is 1 or 2 or... See, lambda
Random
is actually
variable.
the input of this particular function. And we don't worry about the input and output of this function. We only worry about the expansion of this function. And we want the moments out of it. That's it.
Okay.
And see, using for this particular usage of MGF, one result can be derived. So if two random variables have the same MGF, so if you have seen two random variables with same MGF, then the two random variables follow the same distribution. We can conclude this or this particular result follows. So you have one random variable x that follows a particular MGF and another random variable which also follows the same MGF, then the two random variables follows the same distribution. We can actually conclude this using this.
Same distribution as in the same mean and variance and stuff, or like normal with different parameters?
No, same MGF. Okay, same distribution means with same mean, mu and everything, with sigma, mu, everything. Okay. When we have same MGF, okay. Yeah. So.
But we will not be able to make any conclusion on the population. It is just the distribution is the same. That's all.
Just the distribution is same.
Okay.
Okay. Now let's come to this particular distribution. And even professor has mentioned most important distribution.
Yeah, he has given 10 stars, sir.
10 stars. Okay. Okay. So this particular distribution is actually normal 0 with sigma square. So what if x follows normal 0 sigma square? What is the moment generating function of this particular random variable x? See, professor has mentioned while you are sleeping, even though if we wake you, you should be able to tell. Now we are,
Yes.
What is the
e raised to lambda square sigma square by 2.
e raised to lambda square sigma square by 2. Okay, correct. Have any one of you proved this?
No.
I tried, but
So I saw that the proof somewhere on the online, but I couldn't understand actually, sir.
Okay. But it is given as an exercise in the lecture, right?
Yes.
Yes, sir, I have done it.
Acha, Binayak, you have done it?
Yeah, I have done it for the mu and sigma square. Then I have put mu is equal to 0.
Oh, very good.
Yeah.
Even I wanted to discuss that. So when x follows normal, can you say me?
Yes, I can say.
Just tell me if I am correct or wrong.
Yes, sir, it is. I got this answer.
Correct, right?
Yes.
Okay. So if this is 10 stars, this actually deserves 1 star. Okay, even it is good to know if my x follows normal mu sigma square, my Mdf of this particular random variable will be e to the power mu lambda plus lambda square sigma square by 2. So only the addition will be mu lambda. So from here you just substitute mu is equals to 0, you will get e to the power lambda square sigma square by 2. So I can actually prove both, but this is very easy to understand. So let us focus on this, and also this is given as an exercise. So I will try to go halfway, and from there you guys should answer. So for proving this, we need to have two things. So mx of lambda is actually x belongs to support of x, fx of x times e to the power lambda x dx. Correct? So x normal 0 sigma square is actually continuous random variable, right?
Correct.
Shall I prove it or you guys will try?
Go halfway, sir.
Huh?
Halfway.
Okay, let me take you through halfway. Okay, we need fx of x now. So what is fx of x? When it is like normal 0 sigma square?
1 by sigma 2 pi
Sigma.
E to
e
the
raised
power
to the power minus x minus mu.
x minus mu is 0 here.
So x square by 2 sigma square.
Correct. And what is the support here?
Minus
0 to infinity.
0 to infinity, no?
Normal can take all real value.
Achha,
So this is 1 by root 2 pi sigma e to the power minus x square by 2 sigma square times e to the power lambda x dx. Okay. So unwanted terms you can bring it outside. So this is independent of x. So unwanted means which are independent of x. This is the only thing independent of x. You can bring it outside. So 1 by root 2 pi sigma e to the power. You just combine these two. So this is something like lambda x minus x square by 2 sigma square dx. So here a small what I will do is some addition, subtraction, some manipulations I will do, and I know this thing. So I know only this thing. E to the power integral e to the power nx dx is integral e to the power e power nx by n. So only this I know. Correct. I try to bring in these things, in these forms. So what I will do is I have x square by 2 sigma square here. So e to the power okay, I have minus of x by root 2 sigma whole square, and I want this times 2 times I need this. So while I am doing this, so I'm just writing this lambda x, okay? I'm just writing this lambda x as 2 times x by root 2 lambda, and I have another, what all need things to be multiplied to get lambda x. I need to multiply
root
sigma
2 sigma
by root 2 sigma lambda by root 2. Correct? So 2 times x by root 2 sigma times sigma lambda by root 2. If you multiply this, you will get lambda x. You can actually do it. Root 2, 2. This will get cancelled. Sigma will get cancelled. You will remain with x lambda. So why I am doing this is to bring e to the power something 2 square. So I have this sigma lambda by root 2. So what I will do is I will add sigma lambda by root 2 whole square, and I will subtract sigma lambda by root 2 whole square dx.
The next step is not clear, sir.
This particular step is it?
The last step, what we are writing, sigma lambda whole square divided by 2.
So okay, what I did is I just add.
Just before that step, that 2 and 2 gets cancelled and sigma gets cancelled, and it ends up with sigma
forming
x only.
Forming the squares.
Forming the square. I'm just forming the square. Okay.
You're forming the square, huh?
Okay. See, this is a. Take
It is
this
in
as,
power of u only, right, sir?
Huh?
Power of u only. Everything is in power. Of
everything is in the power.
Yes, yes. Okay,
Everything is in the power. Okay.
Everything is in the power, and
so
what is it ends up with?
Yeah, ends up, end result will ends up here. We will end up here. Sigma minus infinite to infinite e to the power. You see, this is a square. If I take minus common from this and this term, minus of x by root 2 whole square minus 2 times x by root 2 sigma lambda by root 2 plus sigma lambda by root 2 whole square.
And there's another term, no? Minus sigma lambda whole square.
So sigma lambda by root 2 whole square. It is there, okay. So now you see, this is like e to the power.
From where x by root 2 sigma come?
Whereby?
Upon second last line, by e to the power minus x by root 2 sigma whole square.
Simplification.
See, this came from here, starting. So here, this x square by 2 sigma square, I have written it as x by root 2 sigma whole square.
Okay.
Yeah.
How can you write that one that way?
How can?
How can you write that way? X minus 2 sigma whole square. E power lambda x minus x square by 2 sigma square. Is that right? That's what it is.
Yeah. So this
but
will
that is transformed into
x by.
So that plus will be minus
root 2 sigma. No. See, I have taken minus common from
minus outside.
So from where you have taken minus common?
Okay. So this is, take this as plus and this as minus. So the first three terms I have taken minus common. Okay.
Only from first three.
Okay. First three terms I have taken minus common,
Mhm.
and this term I have left it as it is.
You put it outside the bracket.
I
Yes,
put
yes,
it outside
yes.
the bracket only.
So you're going to put a whole square there, is it? Minus a whole.
Now x minus, this is like a square minus 2ab plus b square.
Yes, sir.
Now this
Yeah.
is like x by root 2 sigma minus sigma lambda by root 2 whole square plus sigma lambda by root 2 whole square dx. Now you see this is like e to the power x plus y. I can write it as e to the power x times e to the power y. And I can bring this sigma lambda square by root 2 outside because it is independent of x. So this will be like e to the power sigma lambda by root 2 whole square divided by e to the power minus, if I multiply cross multiply it, I will get, so root 2 common, you can take a denominator root 2 outside, 1 by 2, and this
No,
will
1 by root 2 only. Square, okay. Okay.
There is a square outside.
Yes, square.
x by sigma minus sigma lambda whole square dx. Okay. From here you can see this is infinite to infinite, e to the power minus 1 by 2. So this is like x minus sigma lambda whole square divided by 2 sigma square dx. Okay. Okay. See, minus x minus sigma lambda. This is x minus, sorry, sigma square. I just multiplied this x by sigma minus sigma lambda. I can write it as x minus sigma square lambda by sigma. And numerator and denominator, if I split it, I will get x minus sigma square lambda whole square by 2 sigma square. Now tell me one thing. This is like e to the power sigma square lambda square by 2. This is infinite to infinite, 1 by root 2 pi sigma into e to the power minus x minus sigma square lambda whole square divided by 2 sigma square dx. Okay. So this becomes 1. How? Or why?
No.
Because if we put x, it will.
It's a normal equation.
Normal with mu 0.
Normal with mu?
Sigma square lambda.
0, 1. Normal 0, 1.
No, sigma square lambda.
No, it's not normal 0, 1.
It's sigma square lambda. Mu is sigma square lambda.
Correct. This will be normal sigma square lambda with sigma square variance. So this follows, this is the distribution. This is actually the PDF of normal.
Now, how do we get that normal distribution? Sigma square lambda or sigma square?
See, if
Because
x
these
is
need
okay, if
uniform distribution.
no, if x is normal mu sigma square, then fx of x will be 1 by root 2 pi sigma e to the power minus x minus mu divided by 2 sigma square. Okay. If x follows normal mu sigma square. Now we have something like 1 by root 2 pi sigma e to the power minus x minus sigma square lambda whole square by 2 sigma square. So just equate it with this. You get mu as sigma square lambda and sigma square as sigma square.
Okay.
That's it. So from there we get this follows normal. So if it is following normal and if we are integrating it along the support, the whole PDF, if we are integrating with the support, what will we get?
1.
1.
Yeah,
So this
1.
will be equal to 1 and ultimately So this will be the MGF of normal 0 sigma square. So in the same way, you can actually
Sir,
prove.
normally we can understand the normal 0, 1 means if the mean is 0 and the whole curve is 1. But now, how do we really map that one? Can you scroll it up, please?
Okay, yeah.
Yeah, the normal sigma square lambda and sigma square. How do we pictorially represent that one in the normal curve?
Okay, if you wanted to pictorially represent, somewhere this is sigma square lambda, and the graph will
Mean
be.
is
This is
so
how
mean is not at 0.
Mean will not be at 0. Mean will be sigma square
And
lambda.
the area is sigma square, is it? What is the area under the curve? 1 was it?
Area under the curve is 1, right?
Total area
Will always be 1.
Yeah, then can you write the normal 0, 1 and what is the normal 0 and 1 is representing?
Normal
0 is representing the mean and 1 is representing the area under the curve, is it? That's right?
No,
normal
one is variance.
One is actually the variance, standard deviation.
Oh, 1 is the variance, standard deviation.
Yeah.
Okay. Here, sigma square is a variance then?
Sigma square is the variance.
Yeah, that's
variance.
Okay. And lambda is?
Parameter of MGF parameter. Or the input value.
MGF parameter, okay.
Lambda is any parameter, that's it. Any value, some fixed value lambda.
But what professor was telling for normal 0, 1, the equation is e power sigma square lambda square by 2, and that's where we were trying to prove that one. So all along what we are doing, proving that e power lambda square sigma square lambda square by 2.
Correct.
But
we got that as a final.
We didn't get that one. We
got it.
We didn't get that end result, no?
Yes, we got it.
Oh.
We got it, right?
I got it.
So there is this e to the power lambda square sigma square
That's out.
being multiplied.
Oh, okay, since you put the big thing is 1, the one which is outside the integral is the one which is the result, is it?
Correct.
Okay. But it's really going convoluted,
Okay, yeah.
But we are trying to understand, but we are not going to really need this one for the exam, is it?
Nowhere this is necessary if you remember the formulas.
Okay.
If
I mean, if you
in
ask
exam,
me to repeat it, no.
Okay, I'm trying to give you some ideas. See, if you understand with proofs, even I feel, or many will get satisfied, or let's say they will understand better.
Really good derivation.
Yeah, that's true.
That was really great. Good derivation.
And
understanding is probably understanding is probably good, but if you ask me to repeat it, probably that will never happen.
No.
Oh, repeat it. Okay.
It won't.
You may go after you go through week 8 contents. You can actually go through this again PDF.
Yeah, that's probably that's a different exercise.
Yeah.
Yes. Thank you.
You can actually.
Thank you, sir.
Yeah. So even professor gave this as an exercise. Okay. So you should actually prove things.
Yeah.
You wanted to enjoy statistics too.
Already enjoying.
Okay. Fine. Now see that's about MGF and MGFs of few well-known distributions, discrete distributions and continuous distributions. And before getting into CLTs, let us quickly discuss this. MGF when sum of two random variables MGF. How will be the sum of two random variables MGF be? Okay. If x1 and x2 is IID samples of x, and there is a new random variable y, which is sum of two random variables x1 and x2. if my MGF of x is e to the power, expected value of e to the power lambda x, then what is, or find MGF of y. So what will the MGF of y be?
Mx of
It will
lambda
be
whole
x1
square.
plus x2, sir, every time. Like wherever we
Mx
are
of
reaching
lambda whole square.
Yeah, correct.
x1 plus x2.
Mm-hmm.
Like wherever we are reaching e to the power lambda x, so it will be e to the power lambda x1 plus x2.
Correct. So first and foremost thing is what we know, we will just try to apply it. So expected value of e to the power lambda y, and we know y, so e to the power lambda of x1 plus x2. Till now it is okay. Also we can do one more step, expected value of e to the power lambda x1 plus lambda x2, which is e to the power lambda x1 times e to the power lambda x2. Okay. And if you know the properties of expectation, this can actually be written like expected value of e to the power lambda x1, expected value of e to the power lambda x2.
They are independent, yes.
Yeah, till now it is okay. Now we should know what is MGF of mx1 of lambda.
It is expected
It is
value
e to
of
the power
lambda
lambda x1.
That means this is actually mx1 of lambda, and this is mx2 of lambda. Now how are these related to x? So I have
IIDX.
IIDs. So they have same distributions.
Distribution.
We have discussed this result now. If they have the same distributions, they will have same MGFs.
MGF.
Correct. So this particular mx1 of lambda is same as mx2 of lambda is same as mx of lambda. So from there you can actually get mx of lambda whole square. So this is mx of lambda, this is mx of lambda. So mx of lambda whole square. Actually what we got here is, if I am looking at the sum of random variable, my MGF will be product.
Yes.
So if I am looking at the sum of IIDs, I will get the product of that
MGF.
particular MGF. Okay. From this, there is a small topic related to MGF of sample means, but I just wanted to directly go into central limit theorem.
So because that also is.
No, it's not that difficult, I hope. So
you can.
From the lecture itself, you can directly get it. So if there is time, we can actually come back to this.
Sometimes it's confusing.
Huh?
Sometimes it's confusing for calculating MGF of sample mean.
MGF of sample mean, is it?
Hopefully both.
Okay.
Sir? Yeah, please continue with that, please.
Okay, let me discuss that quickly then. So we wanted to look at MGF of sample mean. Okay, what is sample mean? We have x bar. X bar is x1 plus x2 plus and so on plus xn divided by n. So there is a divided by n thing. So it's actually scaling. So we just saw sum of two random variables. From there we can actually get sum of n random variables. So let me give this x1, x2 and xn comes from IID x. So all will have the same MGFs. Okay. So if I look at m sum, maybe let us look at the sum first.
Yes.
Where sum is actually, y is actually x1 plus x2 plus and so on xn. What will be my of lambda?
mx of lambda
Correct.
divided by n.
Yes, sir.
Now, what I wanted to look at is look at the yeah. So it's actually x bar is actually y by n, right? Correct?
Correct. Yes, sir.
Yes, yes, sir.
Sorry, sir, what you said?
So x bar, see, if my y is the sum of n random variables, my x bar
Yes.
will be, if I wanted to write in terms of y, my x bar will be y by n.
Yes.
That's
True.
it.
Yes.
Now I want my by n of lambda. So which is nothing but m x bar of lambda.
Yes.
So for this, how can we do? So for this, so how is it related to x?
So you can find first the x1 by n, and then you can.
We can first find
x1 by n, the Mdf of x1 by n, because x1 we know the distribution for that, IID x. So x1 by n will.
Okay, this is nothing.
It is
but,
just 1 by
yeah,
n of that. So Mdf will be just mx of lambda by n.
Can you tell me one thing?
X1 by n. If my Mgf for x is mx of lambda, then this one will be m of x mx1 lambda by n.
Like this.
Yes.
Oh. Okay. Yeah. Correct. So this is from, okay, we will go by definition only. This will be expected value of e to the power lambda y by n. Correct? So from here, expected value of e to the power lambda by n times y. So from here we get my of lambda by n. That's it. So from here we know my of lambda. What will be my of lambda by n? It will be mx of lambda by n whole to the power n. Simple. Understood? See,
yes.
See, y by y by n of lambda is actually expected value of e to the power lambda times the random variable, right? So here y by n, so the same y by n will come here. So I can rewrite it as lambda by n times y. So from there it will be my of y. So this is actually my of lambda by n. So you can use this thing also. So the same thing we used. Okay. So my of lambda by n is actually expected value of e to the power lambda by n times. So now we know my of lambda is mx of lambda whole to the power n. So my of lambda by n will be replace lambda by n in place of lambda. So we will get mx lambda by n of whole to the power n. That's it. So this
How
will
did
be
you get that whole power in? Going to the 3 steps back, is it?
This one.
Okay.
Using this in place of lambda by n, you just replace with this lambda by n. So we will get mx of lambda by n whole power n. So there are some examples also, I guess. So one example, if we take, let us say x follows. Okay. X follows Bernoulli half, or okay, x follows minus 1 1 with probabilities half. Okay. If I wanted to find the sample mean, so the sample mean thing, x bar will be x1 plus x2 and so on xn by n. So what I want is, so what is the moment generating function for this? Mx of lambda. This is half times e to the power minus lambda plus half times e to the power lambda. So this is e to the power lambda plus e to the power minus lambda by 2. Now this is the moment generating function for this x. Now we want moment generating function of x bar, sample mean. So this is equal to mx of lambda by n whole to the power n. So we know mx of lambda is this. Now mx of lambda by n will be just replaced with lambda by n. So e to the power lambda n plus e to the power minus lambda by n divided by 2. We will substitute that here. So e to the power lambda by n plus e to the power minus lambda by n divided by 2 whole to the power n. So this will be the moment generating function for the sample mean of the distribution x, where x follows uniform minus 1 and 1. Okay. So yeah, if I take centralized Bernoulli will be minus half and half with probabilities half and half. The same thing, write the moment generating function for x, which will be
So from a normal, how to find centralized Bernoulli?
From
any normal, how to find centralized normal?
Centralized normal, you just subtract with mu. Each and every sample you see, if your random samples x1 and x2, I will come to there. Okay, follow now.
Okay.
So half times e to the power lambda by 2. Okay, this will be the moment generating function for this particular random variable x, and mx of lambda by n will be half times e to the power minus lambda by 2n plus half times e to the power minus lambda by 2n, and moment generating function for the sample mean will be this whole to the power n. So 1 by 2 e to the power minus lambda by 2n plus 1 by 2 e to the power lambda by 2n whole to the power n. Okay. So this is how you will get the MGFs of sample means. Okay.
Yes.
Yeah.
Just for a clarification, sir, you can just give hint to me, that will be also fine. Like here my y was defined as x1 plus x2, right?
Here?
Y was defined as x1 plus x2, right? But if my y is defined as product of these random variables x1 into x2, right, then how I will proceed, because it will be in that case e to the power lambda x1 into x2, right?
x1 into x2, correct.
So how I will proceed further, sir?
No,
Just to give
nothing. No, there is no simple formulas for that.
Okay.
So you just have to compute with hand. That's it.
Okay. Got it.
So there are no results that follow with product. So that is why we didn't discuss.
Okay, no, just out of place. Okay, that's why I said that you can give hint only. Okay, thank you, sir.
Okay, let's come to this very important central limit theorem. So what this central limit theorem simply states is, if I have some n random variable, if I have some n random variables coming from some distribution, random samples coming from any distribution, it is actually saying any distribution, even though if it has some mean, we can actually centralize it. So as of now, from any distribution, if you take some random samples, if your samples are very high, if your n is very high, then this particular sum divided by root n. So if I look at the new random variable, which is the sum of those n random variables divided by root n, as n increases, as the value of n increases, or n becomes larger and larger, or we are taking larger, more number of random variables, then my y actually follows my y actually
Normal
follows
distribution.
normal distribution with mean 0 and standard deviation sigma square. Sorry, standard deviation sigma.
Variance
So
sigma square.
yeah, variance sigma square. So what is the central limit theorem? Actually,
if I don't take a square root of n, even if I'm taking n, then it will follow normal distribution, right?
No. If you take n,
No.
it will actually become constant.
Constant, yes, because as n increases, comes to
Goes
0.
to 1.
Sorry.
So it will follow uniform distribution 1.
Sir?
So can you please repeat the central limit theorem again? The statement, please.
Okay. The statement says that if I take some n random variables which follow the same distribution that x follows, or n random variables which are IID x with mean mu, so where x is actually with the expected value of x is 0 and variance of x is sigma square, then the new random variable y, which is the sum of all the n random variables divided by root n, this particular new random variable y actually tend to follow, y will tend to follow normal 0 sigma square, 0 mu with the mean 0 and variance sigma square. Therefore, the MGF of this y actually is approximated to e power lambda square sigma square by 2. So that is what central limit theorem says. And simply, if I wanted to say in one statement, if I have given you any distribution with more than some 30 samples, I can actually approximate that particular distribution to normal distribution.
Yes, I was asking that only, so that n equal to 30. So sir, it brings my next question, sir, just for clarification. Like last Sunday, you demystified y be defined by n minus 1, right? So in the same way, can you say why n equal to 30 is so sacrosanct? It is only based on observation, or there is some
based on observation, based on simple.
There is no mathematical explanation.
No.
It is based on observation.
See, right? some people say n is equals to 25, some say n is equals to 30. Some
Even
say
somewhere I have seen n50 also.
n50, yeah. See, it's actually, we say for
What discussion
any
is going on?
observations, this is becoming true.
Yes. So there is no
What, sir?
mathematical explanation for that, right?
No.
It is purely based on observation.
Yeah, based on
Okay, thank you.
any distribution can be approximated to normal. Okay. So one usage of this CLT is this. So if I have given you some random samples of any distribution, if my random samples are more than 25 or 30, or when n is more than 30, that particular random samples or that particular distribution can actually be approximated to normal.
So I have to do multiple sampling. I have to do multiple sampling for that.
Can you?
Am I supposed to do multiple sampling for that? Like every time I have to pick more than 30 samples?
No, not even. See, this is approximating, okay?
Okay.
We are just approximating it to normal. Okay. Any distribution can be approximated to normal using this CLT.
But sir, this there is some link is missing, right? Say for example, my my underlying distribution is following some zigzag pattern, right?
Okay.
Any pattern, zigzag pattern, right? Now we are saying that if I take 30 samples, so it will start following normal distribution.
It won't start following. It
can be approximated. It can be approximated to normal.
Yeah, normal.
Okay, so what we are saying, the interpretation is that like we can start using the formula related to normal distribution. That's what we are saying.
See, there will be some error if you calculate probabilities or something. but it will actually be more or less, it will be equal to the normal if I.
Okay, okay, got it.
Okay. So what is the usage of the central limit theorem? Let us see. So using this central limit theorem,
Sir,
we
I have a
actually
question. Like converges to normal and converges in distribution to normal are the same or different?
Converges to normal and
like in one of the in this slide of central limit theorem, the sir wrote that y is said to be converging to in distribution to normal.
Converging.
Yes.
Y is said to converge in distribution to normal 0, sigma square.
In distribution to normal is something like the same thing. Actually, y actually tend to follow the distribution that normal follows. Normal 0 sigma square.
So when we say suppose is there something called converges to normal? Is there anything, or it just
converges means actually the word convergence means actually coming
Yes,
closer
both
and
mean
closer to that particular thing.
As samples of y grows, then it
like
comes
suppose
close
if
to
I
normal.
say converges to normal and if I say converges in distribution to normal,
both are same.
Both are same. Okay.
Both are same. Both are same. So
okay, sir.
Yeah. So now we will see how the CLT is useful in approximating these probabilities. How we approximate probabilities using this central limit theorem. So suppose I have x1, x2, xn samples from IID X, where x is with expected value mu and variance sigma square. So here expected value of x is mu, not 0. Okay. Now I look at the sum of these n random variables as the new random variable y. Now if I ask what is the probability that y minus n mu, why n mu?
Because y is x1 plus
expectation
x2.
value of y.
Correct.
Y expected value of y is.
So expected value of y is n mu. So if I wanted to compute some probabilities where my random sample, if my random sample is, how far is my random sample from the mean? So how far means some delta times n mu. So I just wanted to compute this probability. So y minus n mu, y minus expected value of y is being greater than some delta times something. Okay. In order to find this, and I don't know to calculate these probabilities directly because these are continuous or discrete and I just wanted to compute these probabilities. In order to compute these probabilities, what we actually do is we actually know the standard normals distribution, calculating the probabilities of standard normal. And if we have a standard normal, we can actually say we actually know the probabilities of normal, because anyway normal can be approximated to standard normal.
So can you please repeat?
Yeah. So what I am saying is, we know until now we know how to find probabilities or the areas under the curve of a standard normal distribution curve. So this is how the standard normal somewhat looks like. So standard normal is actually normal 0, 1. So with mu 0 and the standard deviation is 1. So maybe this is -3, -3. So how many of you know this 3 sigma rule? Do anyone know 3 sigma rule?
I have an idea almost more than 90% gets
A little bit, so 95 point
95
something.
yeah.
95 point something.
95% probability.
99.5.
99.5 is it?
No, it's 95 something like that.
Even I remember.
Yeah, it is that like 68, then 90, then 95.
68.
95.
Yes.
No. See,
68 is for middle one.
99.73.
Okay, 90.
Okay. So 99.73 is that means 99.73 values will lie inside this 3 sigma or
68, 95, and 99.7. These are the 1 sigma, 2 sigma, 3 sigma.
1.96 is 95%.
1.96
is 95%, I think.
1.96 is 95. Correct. So this is yeah, okay. Anyway, this is unwanted topic, but most of the random variables will lie within the 3 standard deviations, left and right. Okay. So standard normal will be somewhat like this. So we know how to compute the probabilities of these regions using the standard normal table. But what if the distribution is something else other than the normal? So how do we find the probabilities? So that is what we are going to do now. What we are going to do now is we actually approximate that other distributions into normal distributions, and then normal distribution convert it into standard normals. Then we compute the probabilities there, and that probability will be equal to the same probability here. Okay, what we are actually doing is we are actually converting this distribution into the standard normal distribution, and once we approximate this distribution to standard normal distribution, we compute the probabilities there, and we say that particular probability is approximately equal to this particular probability.
So will we take mod, like mod of y minus n mu?
Will we take
mod function, mod of y minus
if we wanted to see the
on
difference
either
on
side,
both
on
sides,
either side, it
on
can
either side you take mod. Okay. So in order to find that, we will do these things first. Okay. Now see, y minus n mu by root n. So this is another random variable. So let me say w. So this is a new random variable w. So y is one random variable which is the sum of all the n random variables. Now this is new random variable y minus n mu by root n. So using CLT, so this will be used. You see, this becomes, if I expand it, this becomes x1 minus. So this is actually x1 minus mu plus x2 minus mu plus x3 minus mu and so on plus xn minus mu divided by root n. Okay. And one more thing is, in CLT our expected value is 0. Expected value of x is 0. If my expected value of x is something mu, in order to convert it, in order to centralize it, what we will do? So in order to centralize this, what we will do? If my expected value of x is mu, I just wanted to make, I have samples as x1, x2, xn. Okay. In order to centralize it, what we will do? We will subtract
minus
from
delta.
We will?
We will
I
subtract
will
the mean
minus
from the
delta to make it 0.
Yeah, we will subtract mu from each
Yeah.
of the sample, random sample, and the expected value of this will be, so expected value of y minus n mu will be 0. You can actually compute it. Y minus n mu, expected value of y minus n mu will be expected value of y minus n mu. So n mu is a constant. Expected value of y is n mu minus n mu, which will be 0. Okay. So the expected value of this will be 0. Now this is a random variable with n samples we have, and we are looking at the sum divided by root n. So if we use the CLT now,
That's for all That's all distributions, sir.
That's can you comment?
That's for all distributions. That's for all distributions.
Yeah, that's for all distributions. See,
Not only for normal distribution. It's for all distributions.
It's for all distributions. If you have any distribution, we are just approximating any distribution to normal distribution.
Okay.
Okay. See, y is a random variable. Y minus n mu is a random variable. Now y minus n mu, look at y minus n mu. Y minus n mu, expected value of y minus n mu is 0. And we have n samples, x1 minus mu, x2 minus mu, x3 minus mu, and xn minus mu. So n samples sum divided by root n. So what CLT, using CLT, we can say that this will be approximately normal
0, sigma square.
0 sigma square.
Yeah.
Understood this? See, in CLT,
Yeah,
in CLT, this, that is the sum divided by root n will follow normal 0 sigma square. So actually we have n random variable sum divided by root n, where that n random variable sum expected value is 0 and variance is sigma square. So this will actually be approximated to normal 0 sigma square. Now what if I divide it by sigma? So the same thing I divide it by sigma.
So again,
Normal
distribution becomes 0, 1.
This will become standard normal. Okay. So this is actually W by sigma. So we are dividing that particular random variable with standard deviation. So that particular standard deviation. So if you have normal 0 sigma square, if you divide it by sigma, that particular new random variable will follow standard normal 0, 1. This you know. Yeah.
Sir, pardon me, last couple of minutes became too dense for me. Can you just please repeat that part about like using the CLT, how did we make it to 0 again?
We didn't use CLT to make expected value 0. In order to use CLT, we subtracted mu from each of the random variable and random variables, and then the expected value became 0. So now y minus n mu is a new random variable with expected value 0 and variance sigma square, and it is being divided by root n. So now I can use CLT on this. This is actually the sum of n random variables divided by root n. So this will follow normal 0 sigma square. And if I divide this by sigma, so if I have normal 0 sigma square distribution, if x follows normal 0 sigma square, x by sigma follows normal 0, 1. Okay. So even this can be proved, but we are lacking of time. So x by sigma follows normal 0, 1. The same thing here also. If y minus n mu by root n follows normal 0 sigma square, y minus n mu by root n sigma follows normal 0, 1. Okay. Now using this, we can actually find the probabilities. So initially we are interested to find the probability of y minus n mu greater than delta n mu. Right. Now what I wanted to do is divide by root n sigma on both sides. Root n sigma on both sides. So this y minus n mu by root n sigma, this is actually follows normal 0, 1. So this will be equal to probability z greater than sigma root n mu by sigma. So root n and this n will get cancelled. So this is 1 minus probability that z is less than sigma root n mu by sigma, and this is something like 1 minus f z of delta root n mu by sigma. So where fz is CDF of normal 0, 1. Okay, this is how we find probability. So we know this value, this particular value we know. So we can compute it from, as now today we have the standard normal table. But initially, in the olden days, they actually used to integrate it. So standard normal, very easy to integrate because we know the integration of e to the power minus x square dx. So as we know that integration, it is very easy to compute the probabilities directly. So using
Sir,
that
can
only,
you do the activity questions 8.2, any
so
one of the questions?
let us do activity questions now. Few activity
Yeah.
questions and we'll move to next.
One question on this.
Question one.
You were mentioning earlier that any distribution can be done, even exponential, which is not really distributed about any axis.
Even exponential can be approximated to normal.
Okay.
See, it's independent of whether it is discrete, continuous, or it is following few already common known distributions. See, actually that is what I'm telling, right? Normal, standard normal is the center distribution. Okay. From standard normal, if you multiply it by sigma with some sigma, that will convert to normal 0 sigma square. And if you add some particular value to every random variable inside that, it will convert to normal mu sigma square. Okay. And that particular normal mu sigma square, so you can actually approximate it to Poisson to binomial to Bernoulli. You can go back like that. So if you wanted to look at discrete.
Okay.
And in continuous also, there are some parameter changes. You can actually make the parameter changes. Some beta or some n decreasing, n is becoming smaller and smaller. Then it will follow some particular distributions. Okay. The key underline is any distribution can be approximated to normal if you have enough samples with you.
Okay.
Okay. If you have 2 or 3 samples and if you wanted to approximate it to normal, it doesn't work.
Okay.
Sir, we are actually looking at distribution of sum of independent random variables, no?
Sum of independent random variables, yeah.
Not the original distribution. So y is,
okay, you are looking at y, right? Once you know the distribution of y, if you are looking at the sum of distributions, if you know Mdf of y, what is Mdf of y here? Correct? If you know the distribution of y, that means you know the MGF of y. If you know the MGF of y, I know the MGF of x.
Okay.
Okay. From there, you will get the distribution of x. If you know the MGF of x.
Okay.
And why are we going back actually?
No, we started with x now.
We started with x, right? We started with x and we are taking sum of random variables. Okay. So why we are taking sum of random variables is just because in order to convert this particular distribution x to normal, standard normal. I'm not going to see.
So we are taking distribution of y means multiple instances of y and distribution of that y. That anyway will be going to be a normal distribution. Whether x is following any distribution, if sum of x's, if we took sum of x's in x follows any distribution, y will anyway going to be normal, no, sir?
Why? How is that true?
Because we are sampling y.
Okay, we are sampling y.
So sampling of y will not depend on original distribution of x, no?
It will depend on original distribution of x. Sampling, see, the distribution of y is actually dependent on x.
Y is dependent on x, but distribution of y is how dependent on x.
Distribution of y is dependent, see, dependent on the values of x. How x is, see, if x is taking only Bernoulli, if x is Bernoulli.
In any case, samplings of y, in any sampling of y, x will be having same distribution. So y will anyway going to be similar, na, sir?
I didn't get. What you are trying to say is, even though x follows any distribution, my y will
Yes.
follow standard normal.
Y will always follow normal distribution.
This is not true. See, from MGFs itself, I can disprove this.
Okay.
So if it is normal, my MGF should be somewhat e to the power mu t plus lambda square sigma square by 2. Right? That is how my MGF should be.
Sir, can I say something?
Huh?
Can I say something, sir?
Sir, expectation of x will always be the same, and y will be the expectation of x. Expectation of x divided by n.
Times n.
Yes, y will be expectation of x times n.
Hmm.
So whatever be the distribution of x, expectation of x times n will always remain same.
Expectation of x times
X n will always remain the same, means similar, and it will always follow normal distribution, somewhat lesser or higher.
No, x bar is a random because his sampling is done. X bar by n, x bar itself a random variable.
That's what I am saying. X bar is a random variable. X bar
so it
will
will
be
not
expectation of x into n divided by n. Expectation of
Yes.
x.
So
So
x
it
bar
will
is
always
constant,
going
is
to be
not
normal,
constant.
na?
Expectation of x bar will be mu.
Yes, yes. And y is always going to be mu. Mu by n.
No. See, expected value of y is actually n times expected value of x.
Yes. Right.
Okay, right?
So,
see, this is actually the expected value of y, not the y.
Yes. Yes.
Okay. So this is the mean of this random variable y.
Yes.
Okay. This is dependent on the mean of random variable of x.
Yes.
Okay.
But whatever be the distribution of x, the mean of random variable x will always remain. Expected value will always be the same, similar, na, sir? It will not vary much.
Yeah, this is actually mu. The expected value of y will also be n mu.
Yes.
Whatever x1, x2, xn are, the expected value of y is n mu.
So, sir, n mu is expected value, then y will always follow normal distribution, sir? Because mu will not change much.
Okay,
means,
so if you have constant expectation, that means your random variable will follow normal.
Yes.
No, that is not true.
Means normal means it will always be constant. It will not follow any distribution. But we are taking y as a distribution. And if
you
we
are
are
saying
taking
y
mu
is
as
a constant value.
But expected is always constant for every distribution.
For every distribution, expected value is constant. See,
sir, we are looking at distribution of y, na, sir. So if we are looking at distribution of y, then y is a variable.
Correct. Y is a variable.
So expected value of y will always be n mu. That's what he's trying to say. Expected value of y will always be n mu.
N mu.
That's what he's trying to say.
No, that is correct. But he is saying that since it is constant, it is normal.
So now the distribution.
That is not true.
No, he's saying now y will follow the same distribution because n mu is constant every time. So distribution, the shape of the distribution will remain same.
What is the big deal in this CLT? Means
no,
it is intuitive that y will follow the normal distribution.
This is not intuitive. See, you are getting concepts in a wrong way, I guess. See, the thing is, if your expected value of any random variable is of any distribution will always be a value, constant value.
Yes.
Okay. It's not only about normal.
Yes, yes. That's what I am saying.
Even it is, see, you are saying my expected value of y is n mu and n mu is a constant.
Yes.
So my y follows normal.
Yes. So we are taking random samplings of y. Okay. Then n mu will vary slightly. If we are looking at y different instances of times, just like we sampled x, we will sample y. And then we will get the distribution of y that way, na, sir? We will going to be sample y.
So we cannot do
then
sampling.
But we are not sampling y,
Yes,
right?
we cannot do
sampling
sampling.
X.
We cannot sample y, no? Y is dependent on x. Every time we have
Distribution of y means just that, na, sir? Sampling of y. How we are getting
No.
distribution of y?
Okay.
Y
Okay.
is just
Let us take one example. What you are saying, very simple example. Okay. So let us say x follows.
Take roll of dice.
Okay, roll of dice. Okay.
Yes, sir.
So I take
X1, X2.
x1, x2. Okay, I roll dice 5 times. Okay. Okay.
Okay.
And I just wanted to after 5 rolls, I just wanted to compute how much score I got. The score will be like the sum of all the numbers appeared on the 5 dices.
Right.
Okay. So this is the total score I got after rolling die 5 times.
Right.
Now what all the values y can take?
Sir, we are observing x1, x2, x2. The y will take expected value of x1 plus expected value of x2 plus expected.
It will be 5 to 30, sir. 5 to 30.
Okay, if you wanted to look at the expected value of y will be 5 times expected value of x. So what is the expected value of x?
3.5.
So what will be the expected value of y?
17.5. 17.5.
So this is actually the mean of this particular random variable y.
Right.
Correct?
Now we are looking at distribution of y.
Now we are looking at the distribution of y, or if you are trying to find the PMF. Here y is actually discrete. Now you just have to find the PMF.
So we will be again conducting the experiment with same x1, x2, x3, x4, x5 n times.
N times.
So we will get different
5 times.
values. We will observe. We got the value 17.5 in one sample.
No,
we will have to sample y multiple times, na sir?
Okay. No, that is not the case. See, this is not for one sampling case.
This is the one sampling of y, na sir? It will be multiple samplings of x, but it is one sampling of y.
See, don't bring sampling into the play, okay? We are done with sampling. Okay, we don't want samplings here. Just talk about samples.
Okay.
So I'm rolling dice 5 times. What all possibilities can it happen? So first time you can die 4. 4 can appear on top.
4, 3, 1, 6.
4, 6 and 6. Okay, 6. Okay.
6, okay.
So this is one instance, okay? If you play one time, this is what your output is. Okay?
Yes.
If you play some other time, your output is something else. Maybe 5, 5, 2, 4, 1.
Yes.
Okay. Instead of taking it like this, so this 4, 5, and whatever the output comes as first time you throw. So this will actually be a random variable, right? You don't know what comes.
So we are summing the random variables, the 4 plus 3 plus 1 plus 4 plus 6 and dividing by root n means root 5.
Wait. See, this actually, the first time you roll a die, this is the output, right? 4 for first time you are getting 4, second time you are getting 5, third time you might get something.
No, this is first time, second time, third time 1. Rows are the first row, second row, third row.
Okay. So you are, see, this is the first time, first row, first time the die, first time you throw the die, you got 4. But you don't know you will get 4 every time you do experiment. My experiment is, so you are playing with your friend, okay? Let us assume you are playing with your friend, and every time you should throw 5 times. You should score total your score. He will throw 5 times. He will totally score. Whoever wins, whoever has the highest score will win. So this is one experiment, or this is the situation we have. Event. This is the event.
Yes.
So one game is one event.
Yes, sir.
Like this, you can play multiple games.
So here, what is x1, x2, x3, sir?
Here x1 is first time you will throw the die, right? First
Means
time
in terms of the figures you written, x1 is 4, x2 is 3, x3 is 1. That
this
way,
is
na, sir?
x1, x2, x3, x4, x5.
X5.
But x1, if you see x1 not always takes 4. For one
Yes, sir.
instance,
Yes,
it might
that
take
I
4.
got, sir.
In the next instance, when your friend throws, it might be 5.
Yes, sir. That I got, sir.
See that we cannot. So that's why the first throw is actually a random variable. The whatever the number comes is actually a random variable, right? Correct. The first output is actually a random variable.
So that way, second output is also a random variable.
Second output is also a random variable. Third output is also a random variable. Fourth
Right,
output is also a random variable. Fifth output is also a random variable.
But sir, we are defining y as the sum of x1, x2, x3, x4, x5.
Correct. So y is the sum of x1, x2, x3, x4, x5, where this x1 is a random variable, x2 is a random variable, x3 is a random variable, and x4 is a random variable, x5 is a random variable.
So sir, our hypothesis is that as we are going to increase the n times, means n games, then the y will be going to be tending to constant.
See, if you are increasing n means you are actually increasing this throws. Okay, these throws.
We can say both ways, no, sir.
No, not both ways. This is how CLD is defined. CLD is defined on the number of samples. No sampling is playing in this role.
Okay. Okay, so that's what the confusion.
No. We are not sampling anything here. We are not taking any different instances or any. We are only considering samples here. Okay. So, and also one thing, if you have constant expected value, that doesn't mean it will always follow normal. Okay, every distribution will have mean, and that mean is constant.
Yes.
Okay. Yeah. Where we are? What are the activity questions? Hello. What are the doubts in activity questions?
Yes.
Am I audible?
8.2.
8.2, yeah. So in
Question
8.2, question 1. Okay. So the question 1 says the average life of a coffee machine is 5 years. So we go statement by statement. Okay. So the average life of coffee machine is 5 years. So that means this is somewhat new. And the next statement is with a standard deviation of 1 year. Also it is given sigma square is 1 square.
Sigma.
Okay. And assuming that the lives of these machines follow approximately a normal distribution, find the probability that, okay, now see, so X represents the life of a coffee machine. And this particular X follows normal 5 comma 1 square. Correct? This is what it is given. So assuming that the lives of these machines follow approximately a normal distribution, find the probability that the mean life of a random sample of 16 such machines falls between 4.6 and 5.4. So many words came in this one last statement, that we have to find the probability that mean life of a random sample of 16 such machines. So we have a random sample. So x1, x2 and so on, x16 by 16. Correct? Where x1 is the life of first machine. So x1 is a random variable that takes the value of number of or the life of first machine. Similarly, xi
Yes.
is actually the life of ith machine.
Yes.
Okay.
So here x is already follow normal distribution, so we don't have to divide by root n. Means 4, I think, in this case, right, sir?
We don't have to divide it by anything. So I will let us go. So we need, we don't need to divide it by root n. So what we actually need is this particular probability that the mean life of a random sample is between 4.6 to 5.4. So what we actually have to find is probability that the mean life, so which is the mean life x bar, is actually in between 4.6 to 5.4. Correct? So this is what we have to find. So once you write down what we have to find, what is given, what we have to find, then it will be very clear.
Yes.
So now see.
First we subtract 5.
Okay, we can do it multiple ways. Let me do it like this. We know sum, right? x1 plus x2. Let us treat this as sum. Now x bar will be, if I wanted to write it in terms of y, x bar will be
Sum of all the 16 lines.
y by 16.
Y by 16.
Yes.
Or this will be equal to probability that 4.6 times 16. 4.6 times 16, 26, 424. This will be
73.6.
73.6. Yeah. So this will be like less than or equals to y less than or equals to 5.4 into 16.
Yeah,
So
it's
this is
86.4.
73.6 less than or equals to y less than or equals to 5.4.
86.4.
Yeah.
Why you multiplied? Why you multiplied 16?
Just multiply
Okay,
it.
okay.
To simplify it.
Yeah, if you simplify it, you will get 86.4. Correct?
Yes.
Now we have y, which is sum of random variables. Okay. So probability that what I want is, I know I have y. Okay. I have one distribution, I know y. If I know y, I know that y minus, actually we have to divide, sorry. Y minus n mu by root n sigma follows normal 0 1, where y is the sum of random variables. We know, right?
Yes.
So just now we discussed here. See, any distribution, even it may be normal also, but the sum, if I look at the sum y random variable, if y is equals to x1 plus x2 plus and so on xn, then y minus n mu by root n times sigma follows standard normal 0 1. Correct?
Yes, sir.
So that is what we do here. So here what we do is y minus, what is n? 16 times what is mu
5.
given? Mu
5.
is given to be 5 by root n is 16 times sigma is given to be 1.
1.
So that means y minus 80
Divided
by
by 4.
4 actually follows normal 0 1. Okay, I have y with me. What I will do is I will subtract it with 80 and divide it by 4. So 73.6 minus 80 divided by 4 less than or equals to y minus 80 divided by less than or equals to 86.4 minus 80 divided by 4. So this is, so this will be minus
6.4.
Oh, sorry, 4
4.
divided by 4. So this particular y minus 80 by 4 follows standard normal. Correct? So this is z less than or equals to 6.4 divided by 4. So this will be probability that minus 1.6 less than or equals to z less than or equals to 1.6. So this will be
1.0616.
So this we studied in week 5. If you remember.
Yes, sir.
Mhm.
Sir. Hello, sir. Are you there? Hello, sir. Are you there?
Well,
Hello.
Yes, sir. Sir, once again, network had gone up.
Yeah. I don't know. Even I am not sure. Is it my wrong with my laptop or is it wrong with Zoom? Okay, I already messaged.
Always that after the assigned hours, it gets disconnected.
Yeah. So yeah, exactly. Even it is following uniform for me.
Yes, sir. Yeah, that's what we are discussing.
So uniform.
I think that's the way it is set up, I think.
I don't know. But how you guys are being in the session more than 2 hours?
Because we are not
More than 5 hours.
Okay. More than 5-6 hours, right? Okay. Okay, let me get the co-host access.
Sir. Till the time you get waiting for access. Now here, as we are giving the reference of week 5, so it is bringing a doubt. Like in week 5, we studied x minus mu by sigma, and that was equivalent to g, right?
That was equivalent to
value of g. We used to calculate g equal to, you can write it down, g equal to x minus mu by sigma. X minus mu by sigma equal to g. Yes.
Standard normal.
Yeah.
So that is what we do, right? Here also.
But here it is square root n and then sigma. So
see, that is where if it is other distributions. You can actually use that thing also if it is normal.
in question fz of 1.6 is given. But minus 1/6, minus 1.6.
Minus 1.6 we will get to know. See, if x follows normal mu sigma square, then x minus mu by sigma follows this. Where we are only talking about distributions, okay? Why we are bringing n into the term is because we are actually dealing with samples here. We are not actually dealing with x. Hello?
Yes, sir. Yes. Definitely.
So we are not dealing with x anymore here. We are dealing with the sum of the samples. Not even the sample, sum of the samples.
Correct.
So that is different from this. Here x is following normal mu sigma square. But here it follows something like normal 16 times 5 and sigma square. So 16 square sigma square something. So 1, 1, 1. So sum of we will look at that thing also. Sum of random variables.
No problem, sir.
Sum of random variables actually follows normal.
Yes.
So sum of independent random variables follows normal. Okay, normal with mean multiplied, it will get multiplied 16 times 5, and the standard deviation is actually 16 times 1 square, I guess. 16 times or 16 square times 1 square. So we will get n square. Okay. So this actually y follows this. Now this now you, if you know this, now you can actually do y minus 16 times 5 divided by sigma. What is sigma? 16. Okay, and this will be only 16. So this will be like 16, root over 16. So the same thing you will get here also. Where? Here. So y minus 16 times 5 divided by root over 16 is nothing but this particular y follows
Normal 0, 1.
normal, no, y follows 16 times 5 comma 16 times 1 square. So this is normal 80 comma 16. So that is why you can directly use this, or you simply use this. In both ways we will get this. Okay, I will prove it in a while. Okay, see here itself we have, if we look at the sum of independent normals, it will actually follow normal.
Sir, fz of 1.6 is given, fz of minus
fz of 1.6 is given, right?
Hmm.
So how we can get fz of minus 1.6 is looking at the symmetry. By looking at the symmetry you can get.
Minus sign.
So yeah,
it will be the same.
Yeah, minus sign. No, minus.
If this is 1.6, this is minus 1.6, and whatever the probability or the whatever the area under this curve will be equal to the area under this curve. Agreed? So probability that z is greater than 1.6 is actually equal to
But we are interested in the unshaded area, no? We are interested in the unshaded area. Is that right?
We are interested in unshaded region, but the connection between fz of 1.6 and fz of minus 1.6 is, you will get it from here. So the probability that z takes greater than 1.6 is actually probability that z is taking less than minus 1.6. These two areas are equal. From here you see this is actually 1 minus fz of 1.6. Correct? Probability that z is greater than
fz of 1.6. 2 times fz of 1.6.
Correct. This is actually fz of minus 1.6. So from here what we will get is fz of 1.6 plus fz of minus 1.6 is actually equal to 1. So we know 1.6, you just substitute fz of minus 1.6 as 1 minus fz of 1.6. So you will get 2 times of fz of 1.6 minus 1.
2 into. Okay.
Okay. 2 into. It will be like 2 into. So just substitute this value and multiply it by 2, subtract it by 1, you will get the answer. So this is how using CLT we can do the problem.
So this was a CLT problem. I mean, distribution.
Okay. Okay. Let us discuss this one thing. We will end the session. As we are going to have one more session, rest of the things we can discuss. Yeah.
You are coming on Sunday, sir?
Sunday, I don't think. Nikita will be coming, I guess.
Sir, can't you take the session, sir?
The continuation will be there, sir.
No, Sunday I will have a session on Max 1.
So then you can take it tomorrow morning also, right, sir?
The continuation will be there.
Not tomorrow.
Tomorrow morning?
No.
Yeah, sir, it's fine.
Oh, fine
Not
for
for
you, but not for
all.
me, right?
It's weekend actually, sir.
See, if I try, I can, but no, not that possible. We can
That
do.
will be hectic, sir.
Or I will try for Sunday session. I will ask max one session someone to take, and I will take.
The continuation will be there, sir.
Yeah. Or else I will, if not possible, I will give the same slides which I have to Nikita, and even she. Okay. Yeah. Okay. Let me discuss this. So this is one good important result that might help us solving problems in this lecture, or solving problems for quiz, or it may solve problems in end term. And also this we will use in future courses, that if I have independent normals, when I say independent normals, I am not saying IID normals, I am saying just independent, not identically distributed. If I have independent normals with me where each of xi follows normal with mean mu I and variance sigma I square. So this tells me that each of the random variable has different means and different standard deviations, but one thing is common, that every random variable is of normally distributed. If I have like that, and if I look at the linear combination of these random variables, so when I say linear combination, that means one constant is multiplied, scaling with summing is what the linear combination means. So a1 times x1 plus a2 times x2 and so on an times xn is a new random variable y. An interesting fact is that this particular random variable y follows normal normal, this actually follows normal. So sum of linear combination of independent normals is normal.
Yes.
So that is what result gives us. So if I combine, or if I sum up normals, independent normals is normal. And this particular normal, it follows normal with mean mu and sigma square, and also we can actually find the distribution, that means all the parameters also we can find. So this particular mu is actually equal to a1 times mu plus a2 times mu plus and so
mu1
on an times mu1 mu2 and so on an times mu1. Okay, this can be easily proved. So expected value of y is actually expected value of this a1 x1 plus and so on plus an xn. So this is actually expected value of a1 times expected value of x1 plus a2 times expected value of x2 and so on. So this is what expected value of x1 is mu1. So that is how it will be a1 times mu1 plus a2 times mu2. And even variance also follows a1 square sigma 1 square
A1
plus
square.
square sigma 2 square and so on plus an square sigma n square. So even this is also a simple proof. When these are independent, that means they are not, there is no correlation between these random variables,
uncorrelated,
and therefore they are uncorrelated. When it is uncorrelated, we can, there is a property of variance. Variance of y will be variance of a1 x1 plus a2 x2 and so on an xn. And if it is uncorrelated, sum can be split into individual terms.
A1
So
x1.
this will be variance of a1 x1 plus variance of a1 x2, like this. And variance of constant times x1 will be a1 square of variance of x1. So even this we know, this is one property of variance. And from here variance of x1 is nothing but sigma 1 square. So simply it will be a1 square sigma 1 square plus a2 square sigma 2 square, like this. So this will actually follow normal. So proof is actually using MGF, we can actually prove this. So take the MGF of these things, and I already told you MGF of this xi will be e to the power mu1 lambda plus sigma 1 square lambda square by 2. So if it is having, so sorry, mu I sigma I square. So take it as an exercise, or if you are interested, you can take it. So take this. This will be the MDF for each of the individual random variables. Now it is sum. We are looking at the sum. So look at the random variable my of lambda. So sorry, the moment generating function of this random variable y. So try to write it in terms of this. You will get it. Hmm? What is that? Are you asking something?
Nothing.
Nothing, right?
It's a disturbance. Sorry.
Okay. Okay. So that is about
Yes.
that thing, and we will discuss this small topics of gamma. And so gamma distribution is one more distribution, which is a continuous distribution, where he say this has two parameters. So x follows gamma alpha beta, where alpha is called shape parameter and beta is called rate parameter. And for these conditions are alpha and beta are greater than 0. So shape and rate looks like a positive parameters. So alpha and beta are greater than 0 here. And one more thing is, the distribution will be, so we don't need exact distribution, it requires a gamma function. So if you know gamma, that is very good. This is gamma of x. So we require this if you want the exact distribution. Constant will contain gamma function. But we are not interested with constant, we are only worried with the how the distribution varies with the value, with the random variable. So it actually fx is directly proportional to x power alpha minus 1 times e to the power minus beta x. And the support of this is actually x greater than 0. Okay, so this gamma distribution will actually follow this. So the PDF of this is directly proportional to x power alpha minus 1 times e to the power minus beta x. As I said, we can actually write fx is equals to constant times x power alpha minus 1 e to the power minus beta x. So this constant actually requires gamma alpha plus beta divided by gamma alpha times gamma beta. So where this particular thing is a function, it takes values for different alpha beta. Okay, so these all are not necessary for us. So it is actually a constant, but so the PDF is dependent on this particular function. So x power alpha minus 1 times e to the power minus beta x, where alpha and beta are the parameters. And interesting facts or the moments of these are mean, which is expected value of x, which is alpha by beta, and also the variance of x is alpha by beta square. And why we are discussing is just because in order to discuss this MGF of this x is pretty interesting to look at. The MGF of this is actually be equal to 1 minus lambda by beta whole power minus alpha. And this MGF is only valid for lambda less than beta. Okay. And till now it's okay. And how we connect this particular thing with our course is, we have studied exponential functions, right? And exponential functions we have studied a lot on the distribution, and we have studied many examples, real life examples on exponential distributions. So actually this gamma distribution is actually the super distribution of super means bigger distribution of this exponential, or one case of gamma is exponential, where if alpha is equals to 1, So in these parameters, in these two parameters, if your alpha is 1, then this particular MGF will convert to and this is actually 1 by lambda 1 minus lambda by beta. So this is and lambda is less than beta. So this particular result we have proved earlier in this class, right? So I said I will use that result again. So that is this result. Where is it? This result. So MGF of exponential distribution is 1 by 1 minus lambda by beta, where lambda should be less than beta. Correct? Am I audible?
Yes, sir. Yes, you are audible, sir.
Yes, right?
Yes.
Okay. So the same result, the same thing follows. Now our MGF has reduced to the form of the distribution of exponential. So this is like 1 by 1 minus lambda by beta, where lambda is less than beta. So this particular x follows exponential beta. Okay, if alpha is equals to 1, our gamma distribution is actually follows exponential distribution. And yeah, okay, then with this we will end this.
Sir?
Yeah.
As the support is greater than 0, right?
Support is greater than 0.
So if we have to integrate, so whether we will integrate from 0 to infinity or 1 to infinity?
0 to infinity. Why 1 to infinity?
Okay, no, greater than 0, no? So I thought.
See, x is greater than 0.
Okay.
See, x is actually different. Alpha is actually alpha, beta are the parameters.
Yes.
X is actually the values that it takes.
Correct. So while integrating, we'll integrate from 0 to infinity.
For integrating 0 to infinity. Okay. Correct. Okay. With this, we will end today's session and we will continue from what happens if many interesting results are there. Some of independent exponential functions will be gamma.
Beta is there, chi-square is there.
Beta, Cauchy, chi-square, and everything we will discuss in the next session.
Sir, we are covering beta, chi-square, everything. Then why are we leaving out log normal and V-will?
See, even studying this itself will be difficult for us.
I know, but log normal, sometimes we hear that that's very common in data science. So
in data science it is common. See, we will not discuss it here. Maybe we will discuss the log normal in machine learning foundations, I guess.
Okay. I also don't have any exposure. I just only heard from friends.
Yeah. Log normal is
very common and all.
Yeah. We will use that. We will study in ML foundations, I guess. Okay, we will see it there.
So are we done with today, sir?
Yeah, we are done with.
We are not discussing all those in this week, right?
We are not?
No, sir. Chi-square we are discussing for this week or next week?
Yes, it is in this week's syllabus. It is in this week's syllabus, no? Cauchy, beta and chi-square. Week 8 syllabus.
Chi-square?
Chi-square is there, no? Week 8.
See, everything is interlinked, okay? This exponential, gamma, normal, chi-square, these all are interlinked to each other. Every distribution is somehow connected to normal.
Actually, you just touched base on. There was not a detailed discussion happened in the lecture, is it?
Correct. It has not.
Just a touch base.
Yes, complete touch base. Complete touch. I was coming to that point.
Even we don't study in the later weeks also. In week 9, we won't study this chi-square distribution.
But sir, if you are coming, then you can throw some more light on that, sir. Because as Mr. Mohan is saying, he is absolutely correct. It was complete touch base. Just 3 or 4 lines are there in one slide.
Yeah. So yeah, in week 9, in week 10 we will use chi-square, but we won't use this beta, alpha, beta, gamma, these distributions.
Even this gamma is suddenly jumping from nowhere.
Yeah. See, that is why gamma we just discussed to discuss the MGF of that gamma and how this gamma is actually related to exponential distribution.
Sir? But there is no bridge between how the gamma is suddenly came.
This is one of the distribution. No, this is one of the distribution we can say that. So once professor is done, so he introduced that there are many more, continuous distributions. So he started talking about 3 or 4 more of them. That's what I got. He said at the beginning of lecture number 4 that there are many more continuous distributions which we have not gone through. So let me start. So we directly jumped into gamma and then beta and then chi-square.
Yeah, I think we are again cram session only. We are going. We are just focusing on how to get the marks. But how are we reaching a point of understanding is a bit difficult now because it's too much of volume.
See, even
too little time and
correct. See, that is why even if I get a short time, I try to explain it with some understanding, with proofs and everything. Because
so that's also please
that
come
will
on Sunday,
give you more exposure. That will give you more exposure or more interest. What I feel is I will get excited or interested if I know how it is being.
Sir, it brings more clarity, sir. So the way it brings more clarity.
Yeah.
Sir, please come on Sunday so there will be continuity, sir.
Okay, maybe I will try to come.
Sir, last Sunday you said that whenever you come next time, as you have come today, so we will discuss a little bit about concentration phenomena, which was there in additional content in week 7. So in that, one of our friend had asked a very valid question. He had said that I will go through that why e to the power minus lambda plus e to the power lambda divided by 2. The upper bound is lambda square by 4, something like that. So this question,
yeah. Why we divide it by only 4?
Yeah.
Why not 5?
So did you get some time to?
No. I didn't look at that. I think
please take a note of it, sir. So,
dividing it by 3.
Yeah, we were discussing that if we take any other function also, so it is coming within that original curve, like e to the power minus lambda plus e to the power lambda by 2. So this is my main curve. So whatever if I am taking in place of e to the power lambda square by 4, that will also fit within that curve only. So why e to the power lambda by 4 only? Then you said it's a valid question.
Yeah, that's a valid question. And that thing I will look at.
Please take
One thing I thought of is like if I divide it by 3, I think it will go outside of.
No, I think then the counter to that was that if it has 6, then also it is coming within.
The least value I can have is 4. Is what
and I think one more question was there, which I am also missing it out at this point of time.
One more question is that even I remember that question. That is related to.
I will go through that recorded lecture and I will put in discourse that there are 2 questions which we are supposed to discuss today.
Related to empirical distribution, I guess.
And concentration phenomena. So these 3 things were there, so that we can.
Okay, we will discuss.
So next Sunday, sir, you can come on Sunday and.
Okay. If I come, I will take. Most probably, I will try to come, or else.
And sir, then one more point, sir. Today I joined, I think 10-12 minutes late. So I don't know whether at the beginning we have discussed or not. We started with MGF, that's very good, sir. But have you given some intuition about generating functions, like why generating functions is needed, and then moment? I have missed it out. I will go through the recording.
No.
Because that kind of clarity is missing in a video also, sir. Because why I'm saying today, why I was just trying to figure it out through Google. So I came across a new term, that probability generating functions. I thought, what is this? We are struggling with movement generating function. I have come across one more term, probability generating functions, PGF also.
Okay.
So that is also some sort of a function only, defined for x is greater than 0.
There's nothing was talked in the lecture, no? Just suddenly bringing PGF.
No, I made it very clear, Mr. Mohan, at the